And I'm pleased to introduce Asan Kamalu, who is a postdoc with Jimmy Lin at the University of Waterloo, got his PhD from the University of Alberta, and has done a bunch of exciting work on question answering, and is going to talk to us about that today. So take it away, Asan.
Thank you very much, Doc, for the introduction. So happy to be here today. It's my pleasure to get to talk to you all. I'm excited to tell you about my work on evaluation and data quality for building helpful question answering models in information-seeking scenarios. Let me start off by this headline, claiming that ChatGPT is better than fund managers. Its source is an analysis that asked ChatGPT to create a theoretical portfolio back in March. They tracked its growth and compared it with 10 other funds. It sounds hyperbolic. If we look closer, it turns out it actually is. But why? Two flaws: limited data and unfair evaluation. The conclusion is made by only one data point. And instead of comparing with best performing funds, the reference funds are chosen based on popularity. This is a toy example of what I'm going to talk about today. Flawed evaluation can happen in research too. The research we learned from the past is that issues in evaluation impedes progress in model development. Similarly, a lack of data or flaws in datasets hinders model development. It would also stop us from working on interesting problems. At a high level, scientific research requires at least 4 key elements: interesting research questions, data, model, and evaluation. They are all interconnected. Without proper evaluation, it is not possible to verify models. And without data, it is not possible to answer interesting research questions. My research aims to tackle challenges in evaluation and data in information-seeking scenarios, which ultimately paves the way for developing more effective models. In this talk, I begin by discussing challenges in evaluating question answering models. I highlight the known issues with the common evaluation methods and how these issues paint an inaccurate picture of model performance in this area. Then I talk about a lack of high-quality data in multilingual information retrieval and introduce a new data set that can be used for training and testing future retrieval models. In information-seeking question answering, the goal is to answer questions over a massive text corpus. The questions here do not depend on additional context. The standard procedure for evaluating question answering models is to perform lexical matching between gold answers provided in a dataset and models' predictions. Two widely used methods are exact match accuracy and F1 overlap that are taken from reading comprehension. These metrics are simple to understand and easy to implement, which contributes to their widespread use. However, we can quickly notice that lexical matching fails. Suppose this question whose answer is a date, but the date can be expressed in numerous ways, and only 2 formats are provided in the gold answers. A candidate may be slightly different, which immediately breaks exact match, but F1 overlap works perfectly. Consider this candidate, which we can see is correct, yet it cannot be exactly matched, but the still F1 overlap is reasonable. Now imagine the candidate 17th century, which we humans consider acceptable. But both exact match and F1 overlap fails to match it with gold answers. So the variety of answer forms break lexical matchings. But the failures are not limited to the diversity of answer forms. They can also be due to an incomplete list of gold answers that do not fully cover all plausible answers. On top of these, generative question answering models may generate long answer statements, which makes it harder for lexical matching to recognize correct answers. We know lexical matching misses some correct answer. The question is whether these failures undermine evaluation. This is crucial because lexical matching is the standard evaluation method and is used many times in the literature. If it does undermine evaluation, as the Lord Kelvin says, if you can't measure it, you can't improve it. And we need to find better alternatives to evaluate our models. The first part of my talk aims to tackle this challenge. To understand how lexical matching failures impact evaluation, we conducted a systematic analysis and information-seeking question answering. As a spoiler, not only does lexical matching underestimate accuracy, but it also fails to reflect a correct relative accuracy for comparison. Our goal is to understand, first, the lexical matching failures. This helps us better understand the errors and provide insights into how to rectify them. Next, how these failures impact evaluating models. In evaluation, sometimes the goal is to measure absolute accuracy. Let's say a company has built a magical question answering model and wants to measure its accuracy to decide whether it's ready for production. So the question is if lexical matching is suitable here. In another scenario, the goal is comparative analysis. Suppose we have a new great model, and we want to see if it outperforms the state of the art. Can we use lexical matching for this model comparison? Let's first take a look at the failures of lexical matching. We conduct an error analysis by asking two human annotators to judge whether a given answer to a question is correct or not. We use a random subset of a widely used benchmark for this analysis. Okay, so the most common errors are when model predictions and gold answers convey the same meaning, but cannot be exactly matched. To give you some examples, when answers are entities with multiple names or include synonym terms, this type of error occurs. We find that nearly 50% of exact match failures belong to this category. Another type of error is when answers are expected to be a list of items that is not fully specified in the gold answers. More than 20% of failures correspond to list-style questions. The next error type are when predicted answers appear at different granularity level than the gold answers. This is often the case when answers have spatial or temporal references. And our results show that nearly 15% of failures are due to granularity discrepancy. The failures can also stem from issues in the dataset, including when gold answers are incorrect, or the question is ambiguous and hard to answer without additional context. Around 14% of errors fall under data quality issues. Now we can clearly see the shortcomings of lexical matching. What this shows is that essentially rectifying some errors, such as ambiguous questions or list-style questions, is not limited to lexical matching and demands extra efforts in the data collection. On the other hand, three categories are the root of around 70% of the errors that occur because of lexical matching. So the conclusion is finding an alternative to lexical matching is indeed necessary, as the errors happen too frequently, and potential alternatives are expected to rectify the mismatches from these three categories. Next, we want to see whether these failures influence measuring the effectiveness of models. So to do this, we reevaluate several models using our human judgment. We compare lexical matching results with human judgment in two scenarios. First, absolute accuracy. We want to see to what extent performance is underestimated. we find that the accuracy of models rise by around 24% on average. This substantial change indicates that lexical matching is not suitable for measuring absolute accuracy. Second, we analyze the comparative performance of models under both exact match and human judgment. We find that lexical matching paints a different picture in the model ranking than human judgment, which means it is not a reasonable evaluation method for measuring relative accuracy. Now let's take a deep dive and then see more details for our analysis. We take a random subset of natural questions open and obtain predictions from 12 question answering models. We select a diverse set of models based on different paradigms. Let me give a brief overview of the models we use in this study. The common paradigm in question answering is the retriever-reader pipeline. First, we pass the question to a retrieval model and obtain a list of relevant documents to narrow down the search space. Then we pass them to a reader model to extract an answer. Okay, here, let's take a quick detour and see how a retrieval model works. BM25 is a classic retrieval model that treats text as a bag of words and performs retrieval based on term frequency in documents. A more recent paradigm is the bi-encoder architecture, in which relevance is determined based on the similarity in a latent space. The idea is to encode queries and documents in parallel. This enables us to pre-compute document representations offline. Then we can compute the similarity between query representations and document representations by nearest neighbor search. All retrievers in our study are based on bi-encoders, and two of our models use a hybrid retrieval model that combines BM25 and dense retrieval. All right, let's go back to question answering modeling. Most models in our study are based on the retriever-reader paradigm. As generative models become more popular recently, reader models have transitioned toward autoregressive language models. This paradigm is nowadays called retrieval augmented generation. In the retriever-reader paradigm, retriever and reader models are trained independently, but they can also be trained at the same time. This is the idea behind end-to-end question answering models. At the time of our study, end-to-end models were state-of-the-art. More recently, with the rise of large language models that are trained on trillions of tokens from a variety of sources, we can directly prompt a model with questions, and the model uses its own parameter as a sort of associative memory to generate an answer. Now that we saw all the modeling paradigms, let's continue with our analysis. We took predictions from the 12 question answering models and compared their exact match accuracy with our human judgment. Here's the exact match accuracy of the models. The lowest accuracies belong to the two closed-book InstructGPT models, whereas EMDR2, that is an end-to-end model, achieves the highest accuracy. Another observation is the difference between the top two models, which is only 0.4%. And here are the results compared to human evaluation. We clearly see lexical matching severely underestimates the effectiveness, as the accuracy of all models consistently surges. The two closed-book models, InstructGPT Zero-Shot and InstructGPT Few-Shot, see the highest raise in accuracy. In terms of relative accuracy, the ranking of models under human evaluation is weakly correlated to lexical matching. Under human judgment, InstructGPT Few-Shot becomes the top-performing model. Another interesting point is the gap between the zero-shot model and the few-shot model, which is narrowed by human evaluation. We'll see more about this later on. Okay, so these results drive us to the conclusion that lexical matching is not suitable for evaluating question answering models. Okay, now we know the lexical matching failures and its major problems in evaluation. What should we do to evaluate question answering models? In this part, I talk about the alternatives to lexical matching. The first alternative that is common in reading comprehension is to cast evaluation as a semantic similarity task. However, we do not have a context in information seeking scenarios. Second, we test the ability of large language models by eliciting a prompt from InstructGPT to verify the correctness of a correct candidate answer. Okay, let's see the results based on one of these methods, InstructGPT eval. The trends here are mostly consistent with human evaluation. A substantial improvement for all models and the highest raise for the 2 closed book models. In terms of relative accuracy, InstructGPT eval shows a strong correlation with human judgment. However, there is one notable difference with human judgment. The zero-shot InstructGPT model outperforms the few-shot model by quite a large margin, which is surprising, and I'll get back to this shortly. Now the question is, which failures automated evaluation methods are able to fix? To answer this question, we did a similar error analysis for automated evaluation methods. We can see that automated evaluation methods amend most errors in the 3 categories I presented earlier, which is good news. For the other 3 categories, while they're better than lexical matching, their error rates still remain high, mainly because gold answers alone are not sufficient for evaluating these questions. So what does these results mean? They basically tell us using InstructGPT as an evaluation method is a great surrogate for lexical matching. So it seems we can declare victory and start using GPT models for evaluation. I'm afraid not so fast. There is one caveat. We investigate why InstructGPT eval favors the zero-shot model over the few-shot one. To this end, we manually examine InstructGPT zero-shot answers that are considered incorrect by human annotators. InstructGPT zero-shot answers are long and tend to include supplementary context, which raises the risk of containing hallucinated content. We identify 47 unattributable answers out of 86 answers. InstructGPT eval accepts 30 of those, which amounts to nearly 10% error. These results highlight that automated methods are prone to misjudging hallucinated answers, which led us to conclude they are not reliable against long-form answers, often generated by language models. So to sum up, lexical matching as an evaluation method is just too strict, despite its widespread use. The good news is using an LLM for evaluation is a reasonable option for short-form answers. Nevertheless, automated evaluation methods cannot detect hallucination in long-form answers. And lastly, our quest for automated evaluation methods that are robust against short and long-form answers continues. Okay, let me move on from evaluation to the next part, where I talk about data that is lacking in non-English languages. Let me refresh your minds about the question answering model. Retrieval stands at the heart of our models. However, there's a lack of resources in retrieval for non-English languages. This is critical because we're missing out on more than 40% of web content that is not in English. The prevalence of English resources in retrieval has had a transformative impact in driving progress, but non-English data sets are significantly lagging behind. Therefore, we are in need of a high-quality, large-scale, and diverse data set in multilingual retrieval. Which brings us to the second part of this talk, a new data set for multilingual information retrieval called Miracle. a collaborative work involving many people. The research question that drove us to Miracle is how retrieval models perform on languages other than English. We aim to collect a high-quality, large-scale, and diverse data set. We recruited native speakers to ensure quality. Our dataset consists of 18 languages from 10 different language families. Miracle is a retrieval dataset, so it basically includes queries along with a list of passages coming from Wikipedia that are labeled as relevant or non-relevant. We collected Miracle in 2 phases. The first phase is query generation. We presented annotators with prompts that are randomly selected from Wikipedia and asked them to write well-formed natural language queries that cannot be answered by the prompt. In the second phase, we collected relevance judgments for the queries from the previous round. We did this by asking annotators to judge the binary relevance of the candidate passages from an ensemble retrieval system. Overall, we collected 78,000 queries and nearly 730,000 relevance judgments that represent over 10,000 hours of annotation efforts from 31 annotators. This plot represents the linguistic and demographic diversity of Miracle. It is easy to spot English as an outlier. Using a rule of thumb based on the number of Wikipedia articles, we can break down these languages into low resource, medium resource, and high resource. Miracle allows us to explore interesting research questions for the multilingual setting. The first question we study is how retrieval models perform on different languages. First, we tried the good old BM25. We observed that BM25 performs well on low and medium resource languages, but its effectiveness declines as the resource density grows. The next baseline is to check whether English as a resource-rich language can be transferred to other languages. For this purpose, we fine-tuned MDPR, a bioencoder model, on the English MS Markup and tested it on Miracle in a zero-shot fashion. And here are the results. Compared to BM25, MDPR struggles in low-resource languages, but excels in high-resource languages. Another baseline is to use separate models for each language that are fine-tuned on the Miracle training data and evaluated on the same language test data. Okay, what we found is that fine-tuning helps low-resource languages the most, but its impact is relatively modest for high-resource languages. And the last baseline is to combine BM25 and MDPR zero-shot using a linear interpolation of their scores. Let's see the results of this hybrid model. The hybrid model outperforms in-language fine-tuning on medium and high-resource languages, whereas in-language fine-tuning leads others on low-resource languages. This is interesting because it basically shows that Miracle is particularly useful for low-resource languages. Next, we study cross-lingual transfer to shed light on the linguistic factors that influence transfer across languages. In this analysis, we trained an MDPR model on one language as a source and tested it on another target language. And here are the results. When different models trained on different languages on the x-axis are evaluated on the target language, which is Hindi. The languages are color-coded based on their relationship to the target language. The first model is without any transfer. It is trained and evaluated on Hindi. This would serve as an upper bound for other models. The next group are models that are trained within the same subfamily, even though they have different scripts from Hindi. The next one is a model that is trained on languages with the same subfamily. I'm sorry, same family. And last ones are models that are trained on entirely different languages from other families with different scripts. Okay, looking at the results, we can realize the orange bars that represent the same subfamily languages, Bengali and Farsi, demonstrate better transfer capabilities than others, despite having a different script from Hindi. Our results indicate that transfer effects only manifest when the languages are closely related. These findings sets the stage for further research in this direction to better understand the transfer capabilities across languages. And finally, we put Miracle into practice by using it as a benchmark to compare real-world retrieval models. We did this by evaluating commercial retrieval models on Miracle to test their capabilities across languages. So we'd like to know how commercial models perform in multilingual settings. And given that we have many options in the open source community, we want to determine under what conditions commercial models are a better choice. So let's see what commercial models are. Many companies started creating their own language models using their own secret sauce and offer access to their proprietary language models through APIs. Each API call typically incurs charges based on the number of tokens in the input text. For retrieval, these APIs follow the bioencoder architecture, which we can use to encode documents into dense representations. Similarly, queries can be projected to dense vectors through API calls. Retrieval can be done as before by finding the nearest neighbors of the query vector over document vector. So basically here, we have the bioencoder model. Instead of hosting the models locally, the models are stored on another company's servers. At the time of our study, we found 3 companies that offer embedding APIs. Unfortunately, OpenAI's model lacked multilingual support, and Aleph Alpha only supports 5 high-resource languages. Cohere is the only model that supports all 18 languages in Miracle. Okay, let's take a look at our results. And this plot would get crowded. I'm sorry about that beforehand. So we used 2 open source baselines from our previous experiments, BM25 and the hybrid model combining MDP R0 shot and BM25. We first used Cohere as a full ranking model. We found that it works better than our baselines on the low resource languages, while it falls behind them on medium and high resource languages. Next, we built something, a natural follow-up to this, a hybrid model by combining Cohere and BM25. This model works even better on low resource languages, but it still cannot surpass our baselines on high resource languages. Lastly, we used Cohere to re-rank top 100 BM25 results. We can see it is a good approximation of the full ranking Cohere model, the green bar. On high resource languages, it even becomes close to the Cohere hybrid model. Our results basically show that the Cohere model performs well on low resource languages and works best when combined with BM25. We also found that using it as a re-ranker is a cost-effective option that is nearly on par with its use as a full ranking model. To recap, Miracle is a high-quality data set which is diverse and large scale. While I presented initial exploration to show its potentials, Miracle can serve as a basis for future multilingual models. In addition to releasing Miracle, we use it as a benchmark in the Wisdom Cup 2023 to encourage participation from the community. And this is basically the gist of the research I've done so far. To summarize, I talked about evaluation challenges in question answering and presented a new high-quality data set in multilingual information retrieval. My goal is to find strategies to ensure reliability in evaluation and improve data quality. Going forward, I'm excited to continue exploring challenges toward building helpful information-seeking question answering models in order to establish trusted users and promote their widespread adoption. I envision three main aspects to achieve this goal. Explainability, to understand why a model generates a particular output. Factuality, to ensure the model always outputs factual statements. And accessibility, to foster open science and diversity. Okay, let me talk about explainability a bit. In information-seeking scenarios, it is crucial to have explainable answers. It is also crucial to know the source from which the answer is originated. In other words, we want our models to be attributable to a given source. Forcing language models to attribute their responses can pave the way to detect and ultimately solve the infamous hallucination problem. Attributability is a major concern in generative search applications. We have recently witnessed many companies and startups like Perplexity AI and Microsoft attempt to build systems that not only can they ground their responses in external sources, they can also link responses to supporting evidence. However, these systems are built on private and closed source data, impeding the research community from exploring this avenue. Which brings me to our recent effort to lower this barrier. We constructed Hagrid on top of Miracle to include explanatory answers and human annotations for informativeness and attributability. Hagrid paves the way for us to study open challenges in evaluation and modeling. To evaluate evaluation in a response, first, we need to make sure it is consistent with its source. Second, we need to detect whether the references are correct or not, and what other relevant references are missing. In addition to these challenges, the answers are often lengthy, which complicates the task even further. For example, the number of references to check increases. And also, there may be sections without any references, which needs to be identified and amended accordingly. Another exciting direction for future is that with Hagrid, we can work on constructing models that are capable of generating attributable answers. Okay, so far, I discussed the importance of attributability in general purpose applications. Nevertheless, in some domains where high recall in search is essential, attributability becomes absolutely necessary. I explained this with a niche example. Imagine we have a conversational model over scientific publications that can interact with users to answer their queries. The key challenge here is to link answers to all relevant sections, tables or figures, or any other artifacts in a publication. This is very much similar to citation recall I described earlier. Providing these references helps users navigate publications easier. The example I mentioned is based on one of our projects that is currently in an early stage. We envision a top-down system that allows users to navigate the publication landscape and enables them to narrow down their scope to interact with a more specific content. This is our visualization of ACL publications using AI tools expector model. Next, answering information-seeking questions require models with the ability to output factual statements. By pre-training on massive corpora, language models are able to acquire factual knowledge to a certain degree. Therefore, pre-training plays a key role in factual behavior of language models. To construct the pre-training corpora, we compile text from a broad range of sources and use it to train a language model. However, recent studies suggest that the factuality behavior of language models correlates with frequency in the pre-training data. One interesting direction is to trace back factual behavior of language models to the pre-training corpus. This presents interesting research opportunities to gain a better understanding of the pre-training data. For example, can we identify useful data sources that contribute more to the factual knowledge of language models? Is it possible to determine data contamination for test instances for which the model performs surprisingly well? For factual statements that the model generates from memory, can we force the model to attribute its output to a proper source? Finally, it is critical to have resources that exhibit worldwide representation. Non-English languages are falling behind in the resources for attributability. So following up on our miracle effort, a future direction could be working toward studying attributability in the multilingual setting. I talked about these aspects for helpful question answering model. By helpful, I mean models that are aligned with users' intent and are able to acknowledge their limits. My vision is to facilitate reliable and safe information access for people all around the world. And I believe helpful question answering models are a great stride toward this goal. With that, I'd like to thank my fantastic collaborators and mentors with whom I was lucky to work. Thank you. I'm happy to take questions.
Thank you for the talk, Ehsan. We do have a fair amount of time for questions. I guess I'd start with one on the first part of the talk. You talked about how lexical match can misstate the relative quality of different methods. I wonder, does that does the mismatch or the mismeasurement of relative quality go away if you control for the amount of training data? So if I understood correctly, the biggest differences, the biggest switches in relative ranking happened between methods that were maybe fine-tuned on a lot of data specific to the data set and might have learned the format versus ones that didn't. Like, so the ones on the left here, I'm assuming have less training data than all of those, all of the other ones. But is that true, or is there more nuance to it?
That's a great question. So I think so. Yes, you are right. The far to left models, they are not specifically tuned on this data set, so their answers are more likely to be different from other models. But even though we set them aside, and those two models, we can see the greatest increase in performance. So that basically means that yes, their answers look very different from the gold answers in the data set. So even if we set them aside, we can still see the difference, the difference between the ranking in the models before and after human evaluation. To give you an example, so previously we thought like EMDR2 is the state of the art as it achieved with exact match 53.2, and we had this FIDKD, which is a retriever reader model stands at around 50%, 51%. And after human evaluation, we see that they are relatively on par. So we can see sort of these sort of changes in rankings. So basically, these models are closer than what it seems in after human evaluation. But their difference is not as visible as the other models that are not fine-tuned on this data set.
Got it. Thanks. I guess for that pair, FID, KD, and EMDR2, do you have any intuition as to why FID, KD improves a lot more under human evaluation than the other one does?
It's basically just these like minor differences in the lexical matching failures. So the most common error is like the semantic equivalence type. So the answers look very much similar to the gold answers, but there is some slight difference that prevents lexical matching to match them. So for example, it just happens that, for example, FID-KD may add some spaces even in some answers that changes this performance. So basically, I would say most of the errors are based on, if I go back to this slide, maybe, yeah. This slide, most of the errors look like something like this. So there are some minor differences between the candidate answers and they are actually correct, but we just missed them.
Got it. Thanks. Other questions?
Could you talk a little bit, Luca here, could you talk a little bit about, for the second part, for the miracle, representativeness of Wikipedia as a good source of multilingual data, because like the quality of Wikipedia degrades rapidly as soon as you move away from English down to, like, you have Swedish Wikipedia and Cebuana Wikipedia are 90% machine translated. Is Wikipedia a good source of like rounded documents, or should we move to something else, I guess?
Well, that's also a great question. Basically, Wikipedia, yes, the English articles in Wikipedia are great and everything, and then as we move toward like less resource dense model languages, the quality degrades. However, there are two things that was interesting for us to collect data based on Wikipedia. First of all, it's the most convenient one. Like all the languages are there, and then most of it's sort of like a parallel data. And then you are absolutely right. For example, for Yoruba that we collected, there is only, I think, around 50,000 articles there. And there are a lot of missing information on like these low resource languages. However, it was the most convenient one. The other one is that a lot of multilingual models, like MBERT, are trained on Wikipedia. So it would present like a great opportunity for us to study those, as we know like how much information based on a specific language those models have seen. So that was another intuition that we followed. But you are great. Yes, you are right about this, that we probably need a better source as we move toward other languages. We couldn't find a great answer to it, so this is why we used Wikipedia, but that's absolutely true.
Makes sense. Sorry, following up on your second point, you mentioned, MBERT or any of these models taking great advantage of Wikipedia as a training source. Should one be concerned while evaluating them for retrieval on Wikipedia? That there is some bias depending on how they're trained, given that they use the same resource, or is it still valid because I haven't seen the query? I don't have an answer, but I'm curious about your thoughts.
Yeah, well, that's a great question. So you are right. So those models already have seen Wikipedia articles, but they are trained based on the mass language modeling. So they are not specifically aware of the task. And so they have an understanding of what's going on in the Wikipedia, but they don't know exactly how to do the task. And then, you can see that even though we fine-tune them on lower resource languages, their performance is not that great, just because we don't have enough data. And so I would say, in terms of worrying about like this would create some sort of data leakage, I wouldn't worry about it. But in terms of quality of retrieval, I would worry about it, because for some of these languages, Wikipedia is not a great source.
Mm-hmm. Mm-hmm. Makes sense.
Hey, great talk. I had a question about the improving this sort of model evaluations. So I assume like these large language models are pretty good at these sort of linguistic variations, like when you just have some small differences in formulation. But some of these other error cases where it's incomplete list or incomplete thing, it feels like you might go into long tail knowledge where I, as a human, if I was annotating it, I would probably go to Google and then research, well, is there support for this answer? And if I can find one, then I will give it a good grade. So is that sort of the next stage of this? We give these LLM evaluators access to some sort of knowledge resources that can sort of research these answers and see if they look valid.
Oh, that's a great observation. Yeah. So what I would say is like some of these, I don't think the data collectors they meant to have these kind of data in this data set. So natural questions is collected from Google search queries, and it's called natural because they intended for the data set to represent the natural style of questions that people ask in real world. So I would say it's okay to include some of those these questions in the data set, but the problem is the ground truth is the ground truth. So during data collection, I would assume that these should be identified and provided enough information in the data set so people can work on it. So for future question answering data set, I would say there should be a special attention to these kind of questions. There should be some steps to identify these types of questions and provide enough information in the data set. For the existing data sets, I would assume something similar as you mentioned. So basically, if we want to have, we have like, let's say, ambiguous questions. So there's no way that we can answer those questions without enough assumptions. So one way would be, yes, going over all the possible combinations of things that can happen and provide them in the gold answer with description. I think it's relatively difficult, but that could be done for especially for list style questions and incorrect gold answers.
Cool. Thanks.
Thank you.
You mentioned in future work wanting to push more for like attributed generation. Is it? I was wondering if you can talk a little bit more about the potential evaluation of attributed generation, because it seems very hard to scale.
Yeah. Yes, that's a great point. So we released this data set like I think a couple of months ago, and that's what stopped us from publishing this work somewhere. So we had problem with evaluating. So obviously human evaluation is something that we can do, but we wanted to provide the something that's reliable. So we have two alternatives to for evaluating something like this. Is just to make the problem easier, so we can just control the situation. One way that we want to work on is to fix the answer and just up until the citation. And for that, we want to compute the likelihood of the correct citation. So that would be one way. So there might be some like issues with that. For example, if we have multiple citations, we have to break down the sentence to different sentences so we can compute the likelihood for each citation separately. The other ones, we have some rough attempts, but they weren't successful. So we tried to use LLMs because it's like, why not? But an example like this is quite difficult because we have to break it down and then somehow match it sentence by sentence or fact, like based on piece of information with ground truth. So far we don't have an answer for that, but we're working on it.
Mm-hmm.
One other question about future work. You mentioned a little bit later the trying to learn about which sources contributed to correct or incorrect answers. I guess when you talk about contributing there, what exactly do you mean? Like, how would you measure whether a given or what technique might you use to measure whether something in the pre-training corpus contributes to a given question answering output?
That's a great question. So there are some studies that provide some methods that trace back errors in the output of a classifier or a machine learning system to its training data. So one of them is influence functions. Basically, they perturb the probability of each training instance in the model, and then they see how it affects the output. And the training instance that causes most changes in the output, that's the way they find it. There are some approximations or some methods to use for like they're called error attribution methods, and they can do that. So there is a recent study by, I think, Anthropic, that they did something similar, and they were able to trace back why like language models are generating a certain output. One of the interesting ones were the mimicking ones. Like they found that when we ask language models to mimic some character or something, those are mostly appearing in the training corpus. And when those we ask them about something that's not in the training corpus, they struggle. That was one of their findings, if I remember correctly. So basically, I would say the error attribution methods and then currently influence functions seems to be something that can be tried. There is one problem with that, is that influence function is very expensive to compute, and it's pretty difficult to scale at the level of pre-training corpus. So there might be some challenges there to how to scale it up.
Do you see this as a way to improve factuality, or is just measuring where the factuality is coming from?
For me, okay, sorry, please continue.
No, I was gonna say like whether like, sorry, as a measure where the factuality comes from, like why the model is confidence in generation, I guess.
Yes, so for me, there is something about the data that I feel is overlooked. So we have like these pre-training corpora that they're giant and they have a lot of information there. One thing that I'm really interested in is what's going on in that data. Like, can we find some patterns in the data, have better understanding of what's happening in the pre-training data that we language models are becoming so powerful by getting trained on them. So that's something that I feel is missing. To give you some example, for some data sets, for example, even question answering data sets that are way smaller, once we start looking at them more closely, we start to see some interesting patterns or some problems with the data. So I think we can do some sort of analytical study just to see what's going on in the pre-training corpus and how it affects the model performance. And then maybe it gives us some insights that we can use to make him better. But for me, for now, this is the first part, mostly like an analytical study to see just what's going on there.
All right, well, we're just about noon, and if there aren't any other questions, let's thank Ehsan again. Thanks, everyone. Bye-bye.
Thank you.